What if you woke up tomorrow to news that the moon had been struck by a massive asteroid? The familiar face of our celestial neighbor, forever changed in an instant. This isn't science fiction. It's a scenario that scientists now say is becoming slightly more probable than previously thought. Welcome back to Cosmic Curiosities, where today we're diving into the fascinating development that has astronomers around the world raising their eyebrows: the increasing probability of asteroid impacts on the lunar surface. To understand this issue fully, we need to examine what's actually happening in our corner of space. Astronomical surveys like NASA's Near-Earth Object Wide Field Infrared Survey Explorer, NEO-EYES, and the upcoming NEO Surveyor mission have been cataloging and tracking asteroids with unprecedented precision. These efforts have revealed subtle but significant changes in the orbits of a distinct group of asteroids in the outer asteroid belt. What's causing these orbital shifts? Scientists have identified several contributing factors. Jupiter's gravitational influence has exhibited slight variations due to the ongoing dance of its moons, particularly the volcanic Io, whose mass distribution has changed slightly due to its intense geological activity. These microvariations in Jupiter's gravitational field have created what scientists call a resonance cascade that's affecting certain asteroid families. Additionally, the Yarkovsky effect, a force caused by the uneven heating and cooling of asteroids as they rotate, is proving to be more significant than previously modeled. As asteroids absorb sunlight, they re-radiate this energy as heat, which can act as a tiny thruster, gradually altering their trajectories over decades. The most surprising factor involves interstellar dust. Our solar system is currently passing through a denser than average region of the interstellar medium. This nearly imperceptible increase in cosmic dust creates additional drag on smaller asteroids, further complicating their orbital mechanics. Combined, these factors have led to a slight increase in what astronomers call the impact probability function for the lunar surface. The moon has been Earth's impact shield since its formation roughly 4.5 billion years ago. Its heavily cratered surface tells the story of billions of years of cosmic bombardment. The largest visible crater, the South Pole Aitken Basin, stretches 1,600 miles, 2,500 kilometers, across an impact scar so massive it could fit the entire continental United States inside it. But impacts continue to this day. Between 2005 and 2021, NASA's Lunar Reconnaissance Orbiter documented the formation of over 200 new craters. Most were created by objects less than a meter in diameter, essentially space pebbles, but they serve as a constant reminder that the lunar surface remains a cosmic target. What's particularly fascinating is that we can actually observe these impacts from Earth. When meteoroids strike the airless moon, they create brief flashes of light visible through telescopes. The European Space Agency's Neliota project uses a 1.2-meter telescope in Greece, specifically to monitor and record these impact flashes. Since 2017, they've documented dozens of such events, with the brightest being roughly equivalent to a 10th magnitude starfate, but definitely visible with moderate amateur equipment. Let's imagine a scenario involving an asteroid approximately 150 meters, across roughly the size of the Great Pyramid of Giza. If such an object struck the moon, it would create an impact visible to the naked eye from Earth. The energy released would be equivalent to roughly 100 megatons of TNT, creating a new crater approximately 3 to 4 kilometers wide. The ejecta blanket material thrown outward by the impact would extend for dozens of kilometers, potentially altering features that amateur astronomers have been observing for centuries. A daytime impact would produce a visible flash brighter than the lunar surface itself, while a nighttime impact would be visible as a momentary new star in Earth's sky, potentially even casting brief shadows for observers in dark locations. For comparison, the asteroid that created the famous Tycho crater, 85 kilometers in diameter, was likely about 8 kilometers across. That impact released energy equivalent to hundreds of millions of megatons of TNT, ejecting material that can be seen as bright rays extending outward from the crater for hundreds of kilometers. You might wonder why we should care about an uninhabited world being struck by space rocks. The answer has several dimensions. First, understanding the dynamics that increase lunar impact probability helps us better understand Earth's own impact risks. The same forces affecting asteroid trajectories toward the Moon also influence those that might cross Earth's path. Second, as humanity plans to return to the Moon with NASA's Artemis program and other international lunar initiatives, understanding impact risks becomes crucial for astronaut safety and infrastructure planning. The slight increase in impact probability must be factored into the design of lunar habitats and the scheduling of surface activities. Third, the Moon serves as a natural laboratory for studying impact physics. By observing fresh impacts, scientists can better understand crater formation processes without the complicating factors of Earth's atmosphere and erosion. Finally, there's the question of lunar resources. Many nations and private companies are eyeing the Moon for potential mining operations, particularly for water ice in permanently shadowed craters near the poles. An impact in these regions could either destroy accessible resources or potentially expose new ones. The scientific community isn't just passively observing this phenomenon, they're actively developing new technologies and methodologies to better understand and potentially mitigate lunar impact risks. Several proposed missions aim to place seismometers on the lunar surface, building on the legacy of those deployed during the Apollo era. These new instruments would be thousands of times more sensitive, capable of detecting impacts across the entire lunar surface, regardless of which side they strike. Complementing these efforts, the Lunar Reconnaissance Orbiter continues its mission to photograph the entire lunar surface at high resolution. By comparing images taken years apart, scientists can identify new impact craters with precision, building a comprehensive database of recent lunar impacts. Perhaps most ambitiously, NASA and other space agencies are discussing the possibility of a lunar impact early warning system, a network of spacecraft positioned at the L4 and L5 Lagrange points, stable orbital locations that lead and follow the Moon in its orbit, that would detect incoming impactors days or even weeks before they strike. Such a system would not only protect future lunar infrastructure, but would also provide unprecedented opportunities for scientific observation. Imagine being able to predict a lunar impact and point every available telescope at the exact location at the exact moment of collision. The slightly increased probability of lunar impacts presents a unique opportunity for amateur astronomers and space enthusiasts. With modest equipment, a 6-inch telescope, a dedicated video camera, and some freely available software, anyone can participate in monitoring the Moon for impact flashes. These citizen science efforts contribute meaningfully to our understanding of impact rates and distributions. Every confirmed detection adds a data point to our models, helping refine our understanding of the cosmic game of chance playing out in Earth-Moon space. For educators, the topic provides an engaging way to introduce students to concepts of probability, orbital mechanics, and the dynamic nature of our solar system. The idea that the Moon, seemingly unchanging and permanent, is actually being reshaped by impacts, even as we observe, it can spark curiosity about astronomy and planetary science. The slight increase in the probability of asteroid impacts on the Moon represents another fascinating chapter in our ever-evolving understanding of our cosmic neighborhood. While the statistical change may seem small, just under 1%, it reflects significant underlying shifts in the complex gravitational dance of our solar system. As we prepare to return humans to the lunar surface later this decade, this new understanding will inform mission planning, habitat design, and scientific priorities. Each new crater that forms represents both a risk to be managed and an opportunity for discovery. The moon's pockmarked face tells the story of billions of years of cosmic bombardment. That story continues to be written today, with each new impact adding another sentence to this ancient narrative. Now, thanks to modern astronomical techniques, we're not just reading this story, we're watching it unfold in real time. Our lunar companion has stood guard over Earth for eons, its gravitational influence stabilizing our planet's rotation and moderating our climate. The fact that it continues to bear the brunt of cosmic impacts is yet another reason to appreciate this silent sentinel in our night sky. What do you think about this cosmic development? Would you be excited to witness a major lunar impact in your lifetime? Do you think we should be doing more to protect the moon as we prepare to establish a human presence there? Leave your thoughts in the comments below, and don't forget to subscribe for more fascinating cosmic curiosities. If you're an amateur astronomer who's interested in joining the lunar impact monitoring community, check out the links in the description for resources to get started. Until next time, keep looking up. You never know what celestial drama you might witness.